Hi, this is a second of a two video recording of the topic on data analysis, specifically data preparation and exploration. In the first video, I went over the coding schema for a survey, how to download data from Qualtrics, label it. Now we're going to examine checking data, editing, filtering, addressing missing data, and finally transforming variables. For this session, for the previous session, we imported a data set that had fast food survey data in it that we brought in, labeled, and then assigned value labels to. We also assigned appropriate missing data codes. Well, we didn't. We saw where we could apply missing data codes. And then we labeled the data, assigning value labels where relevant. This left us with a data set that looks like this. Here's a data set. It has the variables ID, health, 1, 2, 3, the ratings of McDonald's, Chipotle, and Shake Shack, gender, age, location, rank, and then rank, Chipotle, McDonald's, Shake Shack. That's our data set then. This is the labeling exercise we did. Okay. Picking up from that session then, what we're going to be doing now is we are going to go to the next step of checking the data. So once the data has been brought into your spreadsheet software, you still need to check the data for numbers that seem out of character. Okay. There may be numbers that are out of range, logically inconsistent or extreme values. So this process may help us identify issues like that. There are many examples of this, some that might be addressed by looking at things like timestamps or date stamps for your survey. Was the survey completed after the cutoff date? Did the respondent take too short or too long to complete the survey? If you are using a survey software, a typical online survey software, you'll typically get IP addresses of the respondents. If the IP address seems to be outside of the target geography, this could well be because the person is using a VPN, but it's also equally possible that the person is outside of the area, and therefore you should examine the response. If you find responses that show little variance, because you can tell this because for a certain respondent, all the answers are pretty much 3 consistently from left to right. And this would indicate that the person isn't giving much thought to the responses. If the pattern of responses indicate the respondent did not understand or follow instructions, again, this might be seen by examining the data. If you're using a scale to measure a perceptual or attitudinal construct, and the scale contains positively phrased and negatively phrased items, you would expect if the score for the positively phrased item is high, for the negatively phrased item, the score would be low. This would then be, if this isn't the case, that would alert one to possibly that the respondent didn't read the question carefully or didn't understand or follow instructions. When data was transcribed from a questionnaire survey to a spreadsheet, we often saw errors like for a 1 to 7 scale, 11 or 22 showing up. This was typically because of typographical errors. The person assigned the job of coding the data ended up hitting 1 twice instead of just once. Furthermore, there might be responses that are logically inconsistent, person showing low awareness for a brand, but indicating having used it frequently. And lastly, if you feel like responses for respondent have many extreme values, again, that might be a sign that the response needs to be examined carefully. Now, some of these things, if you have a very large number of surveys or across many variables, inspecting individual responses or variables can be extremely daunting. This process can be made easier by using some sort of descriptive statistics to inspect or examine the data. We're going to begin here by examining some of our non-metric variables. So non-metric variables are variables that are categorical in nature. Typically, a nominal or ordinal scaled variable would be classified as non-metric. In our data, we have age, gender, and location. Age, gender, location that are non-metric in nature. So what we're going to do here is we're going to examine frequencies and proportions for these groups to get a sense of any erratic behavior in our data. Now, as we go through the process, I have shared in the slides instructions on how to go about doing this very process. For instance, to construct a bar chart in SPSS using these instructions, you would look for the menu item Analyze. From that, you'll select the submenu Descriptive Statistics, and from that, Frequencies. In the window that pops up, you would do the following, and then you would select bar charts from the Charts button and hit Continue. So these steps will then guide what we'll be doing for non-metric variables to construct some frequencies, examine frequencies and proportions. So let's get right to it. Here's our data set. Our non-metric variables are gender, age, and location. Even though I'm highlighting these variables, it should be obvious to you by now that the Excel type of behavior, from highlighting doesn't really apply here. So highlighting doesn't do anything more than just making it the column gray. So to examine these non-metric variables, I'm going to go to Analyze, like the instruction said, and then Descriptive Statistics. From there, I'm going to select Frequencies. Now, once I do that, you may not have, again, it's possible you're having difficulty seeing these pop-up windows. I'm hoping it isn't the case. But in case you didn't see it, we have a window that's popped up, a dialog box that's popped up, where I'm going to indicate what variables are to be analyzed. We're interested in examining gender, age, and location. So I'll highlight these variables either together, hit the arrow button, or I could do this individually by drag and drop, or even together as a drag and drop. Right? So you can either use the highlight and then select the arrow button, or you can do a drag and drop to move variables over to the right. At this stage, we have moved the non-metric variables of interest over to the right. This will then give us a frequency table because by default, frequency tables has been checked here. Let's also examine some charts. So click on Charts and ask for a bar chart. Okay. Having done all this now, if I continue and then OK, we will get a bar chart and frequency breakdown of these variables. Let's see what happens when I hit OK then. When I hit OK, nothing happens in this window except for the fact that we can no longer see the dialog box. Instead, what we're going to do is we're going to go over now to another window. This is our output window. All the output in SPSS is generated in a separate window called the output window. So here's our output. You can see here that we don't have any missing data for the three non-metric variables of interest, gender, age, and location. We have 2,000 valid observations for each variable. You can also see that the breakdown of gender is heavier on the female side, with 59.3% of the data of females. When you have no missing data, valid percent and percent are identical. When you're missing data, the valid percent is computed out of all the non-missing data, right? So valid percent might be is going to be equal to or higher than the percent numbers. The cumulative percent is just that, the cumulative percentages here. We can see again for age, we're seeing a trend where we're seeing a lot of data in the middle. The 30 to 49 group is the kind of the heaviest group here in terms of representation, and we don't have much representation for the 60 or over group. This is something kind of interesting, or something we might want to remedy, the fact that we have unbalanced age groups. In certain instances, it may even make sense to combine the sparse 60 or over group with the one before that, the 50 to 59 group. We're going to be doing that pretty soon. Lastly, we can look at location and see that for location, the breakdown consists of, notes that most people, about half of our sample is located in Manhattan. The same information can be viewed graphically using bar charts. So here's a breakdown of gender. And then we can go on here, lower down, and see a breakdown for age, and finally location. Okay, that was our first analysis in SPSS, where we are running a simple analysis to look at descriptives for all the non-metric variables in our data set. Now we're going to go forward now and repeat this process for our metric variables. To examine descriptive statistics and charts for our metric variables, we're going to follow a similar set of steps. We're going to here examine amongst our descriptives the measures of central tendency, variation, and shape. Right. We're going to conduct this process using the following steps here. So let me get started then. I'm going to go right over to our spreadsheet view. And our metric variables of interest here are health 1, 2, 3, and the rating variables of 3 restaurants. As I noted before, highlighting doesn't do anything. I'm only doing it to, again, literally highlight what's relevant for us to talk about here. As before, I'll go to Descriptive Statistics and select Frequencies. And then here, we already have gender, age, and location because they're left over from our previous analysis. When you have such a situation, one thing you can do is remove the old information by hitting the reset button. It's a good idea to do this because you may not remember all the boxes to check or uncheck to undo previous analyses. So I'll hit the reset button to get a clean slate. And now move the variables health 1, 2, 3 over to the right. Now, as I expand this window, you'll notice that health 1, 2, and 3 have the variables in square brackets, but the label is specified right next to it. Now, as I noted earlier, putting the full scale item out there can make it a bit wordy and hard to kind of read. But we've tried it out now. Next time, maybe we'll go with a shorter label than the one we have here. Selecting all these variables, I'll move all of them over to the right. And now I'm going to uncheck the box for frequency tape. Actually, I'll leave that checked for now. Under statistics, I will check a few boxes for central tendency, specifically mean, median, and mode. Mean is the average, median is the midpoint, and mode is most frequently occurring observation. It turns out that we typically use multiple measures of central tendency because mean is very susceptible or is biased by outliers. On the other hand, median, and if the mean and median diverge, then you know that there is probably an outlier at work here. It's a good thing then to examine all of those 3 statistics. In addition, we'll look at measures of dispersion, standard deviation, and variance, the classic measures of dispersion. Range is the difference between min and max. We've got min and max here. Lastly, we'll also gather data on distribution, specifically skewness and kurtosis. Having gathered all these, let's also pull some charts in. Specifically, let's get histograms in here, along with an overlay of a normal curve. This will allow us to see if our sample distribution is, bell-shaped or not. Bear in mind, in a previous session, I spoke about your distribution you're seeing of your data in the sample specifically is not a reflection of the distribution of the sampling means. Right? That distribution, it will approximate to normal as the sample gets larger. And that is the basis for inferential statistics. something we'll examine in a later session. Okay, now I am leaving this box display frequency tables checked for now in this analysis because I know that we don't have too many discrete values to consider. If you have a metric variable with many discrete, many unique values, you're going to get a very long table. For example, if you have a variable like sales you're examining, sales could be 34.621 million and 57.214 million, so on. So if you have many unique values, the frequency table can be quite uninformative. Right? In this case, I'll leave it checked. Having done all those, let's take a look at our, let's go over to the output window to examine our statistics. Here's what we have. We can note here that for the 3 health 1, 2, 3 variables, we don't have any missing data, nor do we have missing data for the 3 ratings variables. You can see that concern about health is in general has a higher average than those of the other 2 health variables. You can also see that for health 1, there's not much of a difference between the mean and median, but for the other 2 health variables, the differences are larger, which is telling me that there might be an outlier at work for the other 2 variables. Similarly, for McDonald's, we see that there might be outliers here, but less likely to be a case for Chipotle or Shake Shack. The standard deviation and variance are related as one is square of the other. The square of the standard deviation is variance. We can tell by looking, so we can only look at just one of the 2, don't have to look at both. We can tell here that there's more dispersion, more variance for health 1 than there is for the other 2 health variables. Similarly, for McDonald's, there's haters and lovers, more so than for Chipotle and Shake Shack. Lastly, we can examine measures of skewness and kurtosis, which tell us something about the distribution. Specifically, is it balanced or bell-shaped or not? Big deviations of kurtosis, numbers like this one here, that get really far away from 0 in case of skewness, is telling us that the data is leaning left or right, and for kurtosis is a measure of how is the data very peaked or very flat, the distribution that is. Let's go on now and take a look at the picture that's going to tell a better story about skewness and kurtosis. Here we are with our histogram of health 1 variable. You can tell here the distribution is quite, it fits fairly well within the normal curve. This one less so, fitting the normal curve. We can see out here that the normal curve is, this one's sticking way out here of the normal curve. The curve as such, it seems to be have a long tail on the right. So not as balanced as the first one. This one a bit more balanced, but still you can tell there's a bit of a tail on the right side for this distribution also. Going on to McDonald's, we can tell here that, there's this, we're seeing this sort of like people are scoring either high or low. A lot of people scoring on the low end and some scoring on the high end. The Chipotle distribution is a lot more balanced. Same you can say for Shake Shack also. Okay, so far we've examined some descriptives for both non-metric variables and metric variables in our data. Let's go on and examine what do you do if you have problematic data. Well, there are times when you may want to edit your data. Even after you've gathered the data, there are instances where you might feel like, maybe I want to fix this data. Like maybe contacting the respondent, or in some case, secondary data going back to the source. If the data is problematic, then one simple solution is to mark it as missing and leave it at that. Another alternative is to delete the data for respondents with problematic data altogether, get rid of them altogether. Now, there might be times moving along now, we're going to examine instances where you might want to examine data for one group or for certain, based on certain ranges. This is, so one way of doing this, accomplishing this is to filter your data. Yeah. So, for instance, the research is interested only in, the respondents from one area, like New Jersey, let's say. Right? In this case, they might want to filter their data. Let's take a look at how you can accomplish this within SPSS. Specifically here, we're going to do a filtering exercise. We are going to select one level of respondents, males. And when we are done, selecting males, we'll examine the data and then undo that process. That's the last part is really important to remember. So let me go back to our SPSS window and take a look at what this is. So imagine now in our data, we have here the gender variable has 1s and 2s. You can also see for sure, be sure here that the 1s are male and 2s are female. You can see out here that that the first person is male, second, third female, so on. Now let's say that we want to focus our analysis on just males. In that case, you want to select all the males and not the females. One way to accomplish this is to go to data and here say select cases. Within SPSS and many other software too, observations or rows are referred to as cases and columns as variables. And it's kind of important for me to kind of emphasize this part here, that SPSS is rigid about structure. So while in Excel, for instance, you can either swap the rows and columns, quite easily. Within SPSS, this is not permitted. Variables must be along the columns and observations along rows. Okay, so when I hit the data select cases, a window pops up, and here is where I can specify a condition. So the variable of interest here is gender. I'll select gender. And now from the right, I'm going to select the radio button for if condition. And then I'll click on the button for if, which will pop up yet another window. In this, second window within a window, or dialog box within the dialog box, I'm going to specify here gender equal to 1. You might be wondering, why don't I say gender equal to male? Well, because male is a value label. 1 is how the data is coded. Anytime you do a filter or do such analysis, when you're communicating with SPSS, SPSS wants to know the language of the data, not the label. The label is meant only for reports. So now you can hit continue, and this will have selected, as you can see here, gender equal to 1. If I now go on to hit the OK button, it would have filtered out unselected cases. That is our kind of our default here. So okay, let's see what happens. Now, when I do that, you'll notice something happened in the output window, but that's not relevant. In this case, we specifically want to select data based on some criteria. We want a spreadsheet to reflect our selection. So if you look at our spreadsheet, we can see here, row 1 has males, row 4 has a male. In fact, we only have data for males here because that's what we've done. So female data is not being reflected or shown at all. If you were to conduct analysis like compute means at this stage, it would only give the mean for males. All the data would be about males only. You'll notice one more thing out here. Whenever you conduct a filter, a new column called the filter column is created. And this is automatically labeled as selected for the rows that are selected and not selected for the rows that are not selected. In this case, of course, we are only showing the selected rows or cases. Now, this part is really critically important. Let's say you decide to put the magnifying lens on males, examine the data. Now, when you're done doing this, it is critically important to unselect. That is, make sure that you get back all of the data, that you don't just leave the filter on. You got to make sure you turn the filter off, just like a light switch. If you turn it on, you must turn it off. So let's go back to data, click on select cases here. And now I'm going to select all cases. When I do that, notice what will happen on the data view. The data view now shows us we have data again for males, female, and so on. So we have all our data back again. As I noted earlier, notice the filter column now has some selected and some not selected elements in there, reflecting our earlier filter. You can leave that as it is, or you can clear it away. I'll just leave it the way right there. Okay, so that's a kind of a vital kind of important thing to be able to do, is to compute or construct a filter. Now, I didn't actually examine descriptives for this group, but you could have done this. So after setting the filter, you could examine descriptives and then unselected. Actually, it's not too hard. Let's just do it again. Let me go back in there and do this again. So data, select cases. So we're repeating our task here with gender equal to 1 selected. We are going to run some descriptives out here. Like, for instance, we can examine all these descriptives for our metric variables, which we ran earlier, which has been saved. Rerun that. Now, if we go to the output window, it's going to show us information only for males. So all the numbers you're seeing right now are only for males. These averages and so on are only for males. You can be sure about that by noticing the number of cases is far lower than the 2,000 we have in our data set. Now, not to forget that important thing to do, to turn that light off. Data select cases and select all cases. There you go. All right, let's go back over to our next bit of work to do here, is examining what to do if you've got missing data. Whenever you've got missing data, the very first thing to do before you even think about dealing with it is to figure out the why of it. Why is the data missing? The solutions for addressing missing data rely on a understanding of the nature of and the cause for missing data. If the data that's missing is completely random, or the reasons for missing data are completely random, then there is no problem in using some imputation algorithm to plug in the missing values. On the other hand, if the data is missing for some really good reason, like a data deficiency reason, consider, for instance, a questionnaire that had a question for gender that was left unanswered by many people. Now, what if this question was unanswered, not because people just were lazy or didn't have the time, it was because there were some folks who are non-binary and they did not know what to choose. So in this case, it turns out that anybody who didn't answer the question does not fit within traditional male-female categories. And so the missing data is for a very good reason, and it would be wrong to simply make guesses about somebody being male or female here, and to, in that way, plug the hole. So imputation would not be a good idea in this case. Lastly, there may be specific causes for missing data, like the nature of the question. Maybe anybody who was, concerned about the privacy, or in general, kind of cautious kind of people, decided to not answer certain sensitive questions in a survey. So then, missing data reflects the perception of those people, or their angst, or their fear of some sort. Right? So again, Imputation is not recommended in this case because the data is missing for some very good causes. Now, if you know the data is missing for something totally random, then you can go ahead and think about some way of addressing the issue. One simple way is to ignore the data, right? And so you could ignore the data, the missing data point. In some cases, you might want to ignore a pair of variables that are being, connected or linked together. Or you might decide, or what's very common is to do list-wise or case-wise deletion, when an entire row of data is dropped altogether. Yet another option is to encode missing data. We assign an identifier. So for all the variables that are missing data, we'll create another variable that will be a 0 if we have if we don't have data, and 1 if we do have data. So we'll have sort of like this dummy variable that'll basically identify a variable as being a row as having missing data or not. Okay. Now, there are, of course, situations where you might decide to impute the missing data, and that's what we're going to focus on here next. How do you impute missing data? So let me first go ahead and create some missing data. We're going to make a new variable called Chipotle missing with some missing data, and we'll see, how well we are able to impute that missing data. So I'm going to go back to our spreadsheet, and here is Chipotle. So what I'm going to do here is I will copy this whole column, and I'll paste this over here. Didn't work so well. Okay, let me go to variable view here. It might be easier to do it here. So let's copy Chipotle and paste it here. And I'll call this Chipotle. And now I'm going to go back to data view to verify that this actually worked out. It didn't actually work out. So good. Let me try that one more time then. For some reason, I'm not having a lot of luck here in doing a simple copy paste. Okay. So I'm going to take a different tack on this. Okay. So again, bear with me here. For right now, this is probably the better way. I was trying to avoid this. I figured Spss would be more, would allow me to simply do copy paste. But so we're going to spend more time doing this later on. So for right now, don't worry too much about the specifics of how I'm creating this variable here. So I'll go to transform compute variable and make this new variable here Chipotle missing, and just basically specify Chipotle missing is the same as Chipotle. Right? So I gotta make sure I spell this correctly. There it is. And that little bit of transform compute gives us a new column called Chipotle missing. It has decimals out here. Let me go to variable view and make sure it looks just like a regular variable by removing the decimal places. Also make the width narrower, doesn't need enough space. 1 is enough. Okay. Here we have the Chipotle missing, looks very much like Chipotle. A little far apart, let me get them side by side. Easier to compare them then. Here we have our two variables now, Chipotle missing and Chipotle. Actually, okay. There we have it. And so now you can kind of see here, you have Chipotle missing. I'm going to make this variable. What I'll do here is I will create the missing data here in Chipotle missing by deleting the rows observations 1 through 10. So we've kind of simulated some missing data here. Our goal now is to figure out what the numbers are going to be for Chipotle missing. We don't have data here. If this data was missing completely by random reasons that are random, then we could impute the missing values here. And before I do that, let me do one more thing. I want to make sure Chipotle missing is also a scale variable. Smaller also. All right, back here. So let's go. So now to figure out these, impute these missing values, we're going to do the following things. We're going to follow the steps in the missing data slide. I'll go to transform, replace missing values, transform, and I'll say replace missing values. And here I'm going to specify the new variable, which is going to be, well, Chipotle missing is what we're going to do this on. So our new variable will be called Chipotle missing _1. And the method we're going to use, our new variable could be Chipotle imputed, right? Chipotle imputed. This could be as simple as using series mean. So what does that mean? It could also be, some sort of nearest neighbor type method, which is also possible. Let's go with the simplest option out here. So new variables will be going to be called Chipotle imputed, and the missing values will be computed as being the average of the series. If I hit OK now and look at our data view, you'll notice Chipotle imputed has been computed. That rhymes. Okay. So Chipotle imputed is right here. You'll notice all our imputed values are 4.0. That's because all that we've done is replace the missing values with the average for the entire Chipotle missing column. So the numbers are identical. Clearly, they are not the same as the true values, well, except for one. Okay. So there are, of course, many other better imputation methods available than the very simplistic method I've considered out here. One of them is, let's see, there are maximum likelihood estimation methods available and model-based methods available for doing imputation. I'll show you where these are and stop at that. We won't go any further into this section. So you could, with an SPSS, go into Analyze, and here there's an option called Multiple Imputation. And here's where you can specify how to impute missing data values using other more sophisticated imputation methods. Okay. Let me move back to our slides now. So then we have now examined missing data values, of how to impute missing data values. Let's move into now the part of transformation. So data seldom comes in an analysis-ready format. To derive insights, you frequently have to convert the data into a different form. These transformations can open a whole ecosystem of possibilities, or open a lot of opportunities for analysis of our data. And so you really want to spend time here thinking about variable transformation. So here are some common variable transformations to consider. One of them is using units of variables. Let's say your data is in Celsius and you want to convert that to, you Americanize your data, but converting it to Fahrenheit. So you apply a little arithmetical transformation to Celsius to convert that to Fahrenheit. Another one is standardizing or mean centering a variable. This is done to ensure all the data has the same average and a variance of 1. And that's standardizing or z-scoring your data. You can also think about, in some cases, combining different levels. Like, for instance, if you've got a certain category that's very sparse, you may want to combine a bunch of sparse categories into a larger category, or combine a sparse category with a more dense category of a categorical variable. Dummy coding is another thing. Fixing a skew distribution can be done by certain transformations. Binning a variable is a possibility, and sometimes you might want to think about combining different variables together. You may also want to conduct data reduction techniques like principal components analysis, something we'll look at in a later session. Okay. Let's go on and do some very simple data transformations out here. The first one we can look at here is how to change units of your data. So let's focus on the Chipotle reading data alone. So we have here our Chipotle variable is scored on a scale of 1 to 7. What we're going to do here is convert that to a -3 to +3 scale. Here's Chipotle, and we're going to change this variable from what it is right now to a -3 to +3 scale. So let's do this. To do this, what we can do is we're going to go to we'll do some simple math for this one. So let's just think about the process involved out here. We have here a variable that has numbers. Let's write this out. A variable here that is values 1, 2, 3, 4, 5, 6, 7. We want to make this to be -3, -2, -1, 0, 1, 2, 3. Okay. So the benefit of this changing the scale is, well, you know, the midpoint is 0, and so stuff that's bad is negative, disagree is negative, and agreement is positive. Okay. So whatever the reasoning behind it. Now, one simple way, there are two ways to go about the conversion. Okay. One is you could tell SPSS when you see the number 1, make that a -3. When you see a 2, make that a -2, and so on. Or you could do some arithmetic with this. It turns out if you take all the data on the left and you were to subtract, so if you were to do, a different color here, do -4 for every one of these, you would get what's on the right. Okay, so we use a neat little trick here to transform our data. Let's go into transform. And notice I'm still in the variable view. Let's go to data view. It doesn't matter though. We could do this from the variable view also, but let's go to the data view because it's familiar to us. So transform, compute variable. Here I'm going to specify our variable as Chipotle view. And that's our target variable. Now, as you write the name out, you want to be careful to follow the variable naming convention. So no numbers at the beginning, no special characters, no spaces, so on. If you do commit an error, of course, SPSS will alert you with an error message. And here I want to say something like, it's Chipotle score -5. Now I could type out Chipotle, but it's never a good idea to type stuff out. You're always better off moving a variable from left to right as follows. This ensures you don't commit a typo. Now, another thing to note is it doesn't matter when you write the arithmetic expression out here how much white space there is. You could have all the white space you want in the world, it doesn't matter. Okay. And I'll say okay. So our new variable looks as follows. We have another column out here, Chipotle new, numbers 3, 3, -2, and so on. Let's take a look at a frequency distribution to compare the two variables. I'll put frequencies out here, reset. We'll compare, look at Chipotle new and the original Chipotle. We'll examine our frequency distributions for these two. Okay. Here is our output. You'll notice out here that the new Chipotle variable has numbers -3 and so on. The percentages are identical. 1 is and -3 have same percentages. 7, for instance, is 9.8%, and that's a 3 on this scale, 9.8%. Okay. All right, so that's something that people might want to do is to transform a variable, change the units of the variable. In this case, we're creating sort of like the midpoint is 0. Okay. Another common standardization is what is called converting a variable to z-score, or where you're or standardizing or normalizing your variable. This involves converting the variable to another one which has a mean of 0 and a standard deviation of 1. So what we're gonna do, we'll do this for health 1. Right? So let's do this. I will go over to our spreadsheet view, and we'll go back here and let's get to work. We're gonna do this with health 1. Health 1 here it is. What we'll do here is we'll say analyze, and we're gonna navigate to the menus to descriptive statistics, then move to descriptives. In here, I'm going to move the variable, where is health 1. If you feel you can't see the full variable, you can always expand these dialog boxes. Move health 1 over to the right, and now I'm going to make sure that I do one little thing. Check this box. Checking that box will save the standardized values as variables, and that's it. Nothing else to do here except that. So, okay. And now we'll see in the data view, we have, excuse me, a new variable called zHealth1. It's a z-score, which is a standardized form of our health1 variable. To verify that it all worked out well, let me go back and look at descriptives, frequencies, and I'll reset this. I'll get health1 and the zHealth1 in. We'll examine the mean, median, mode, standard deviation, variance. Actually, it's all we really need. I'll just compare those two. Okay. And I'll uncheck the box for frequency tables this time. Heading over to our output window. And notice here is on the left is health1, on the right is a z-score for health1. What's common across these two scales is you will notice the number of observations is the same, but the mean is very different. One has mean of 0, standardized 1, and standard deviation of 1. Okay. So there are instances when you want to standardize your data, and here's how you would do this. Moving along, there are times when you want to combine many levels into fewer levels. This might happen because you end up with a sparse category. If you recall, let's go and take a look at one of our variables. If you recall, when we ran a frequency distribution for, reset this, for age, we noticed something strange. We notice for the frequency distribution for age, when you look at the output, you'll notice we had a sparse category. We had a category here of 60 or over people. That was a very small percentage of the overall sample. So what we're going to do at this stage is we're going to combine the 60 or over people with the 50 to 59 people to make another category called 50 or over. Here's how we're going to accomplish this then. We'll go back to our slide. And we're going to do this through the transform recode option. Now, very important to remember to recode into different variables. If you don't do this, it'll overwrite the original variable and you won't have the original variable anymore. We're going to do this by mapping our data. Let me just write out our mapping process then to be very, very clear about how we're going to go about this. So, I'm going to open up an Excel spreadsheet so I can write this out more clearly and show you how we're going to map the old to the new. All right. Bear with me just one sec. And here is the Excel spreadsheet. And imagine our old variable now is age, and that age has categories. Let's see what the categories. We have 18 to 29 and 30 to 39, 40 to 49, 50 to 59, 60 are over. So these, of course, are the value labels. The original codes are 1, 2, 3, 4, 5. We want to make another variable called h2, right? And h2 is going to have the same labels for, we want to basically have 50 to 59 and 0 over lumped together. So what we can do is we recode this as being as follows: 1, 2, 3, 4, 4. We recode h to h2 as follows. We would, in a sense, be lumping together 50 to 59 and 60 over into one category. So we would then we'll set up our labels separately as follows. Our labels could be 50 over. This is what we'll be engaging in now to transform or recode our data into different variables. So off we go to SPSS to accomplish this. So we're focusing here on the variable age here. Again, highlighting is merely cosmetic. And I'm going to take the value labels away because that might be a little confusing. Here is our original variable. Transform, look for recode, not same variable, but different variables. And now in the window that pops up, I'm going to specify the old variable, input variable, and the output variable. Our input variable is age, output variable is age2. The question mark means SPSS is waiting for us to enter in a, and then new variable, output variable. I'll call this age2. And now if I go ahead, nothing will happen. I've got to hit the change button to make age2 go in. So now we have provided information about the new and the old right here. Next, we got to specify the mapping by clicking on the old and new values button. Doing so takes us to another window where we can specify the old value and the new value. If you recall, our mapping was as follows. Our mapping was 1 goes to 1, 2 goes to 2, 3 goes to 3, 4 to 4, and 5 to 4. You can repeat the same process here within SPSS. Here we are. 2 goes to 2, 3 goes to 3, okay, 4 goes to 4, and 5 goes to 4. Here we have it. We continue, and we have basically specified now whatever is in 5 goes into 4, and our new variable is right here, h2. You can see in data view, we have now a variable called 1. Let's go ahead and go to variable view. Let's call this age with only 4 categories, 4 levels. And I'm going to copy, I would wonder if I can copy this over, save a lot of effort. It worked out good. And we have our last category, which is going to be 50 or over. It said I didn't hit change. Okay. Okay. There we have it. Now what I'm going to do is we have age and h2. We're going to take a look at if our exercise worked or not. Before that, a few more changes, cosmetic changes here. Decimals, and should be good. All right. We'll go to analyze, descriptive statistics, frequencies. We'll examine age and h2 side by side and see if our work has done the trick. There we have it. We have age and h2. Look carefully here. We have in the previous age, we had 15.5 and 1.9% in the 50 or over group. Now they're combined into one larger group. Bear in mind, there's some rounding error involved. That's why the numbers don't add up just exactly, because we only have 1 decimal position shown out here. Okay. Moving along then, we have then also done combining levels. Let's go on to something related, which is dummy coding. Now, dummy coding is often done when you want to work with nominal scale variables. Sometimes you don't have control over the kind of data you're going to get. You get nominal scale data because of the question, the way the question was asked by the researcher. In other cases, the data is just by nature nominal scale, like, you know, what zip code or what area, what city somebody lives in. They are just by nature nominal scale variables. Nominal scale variables with more than 2 levels cannot be used in certain kinds of analysis in their native form. You think about it, the reasoning is as follows. You look at a variable like location. We had essentially 4 location values. We had values 1, 2, 3, and 4 that refer to Manhattan, Queens, Brooklyn, and New Jersey. Now, these numbers are merely unique identifiers. They're not meant to reflect any ordering or you know, rating across those 4 groups. So, however, if you were to run something like correlation or regression, the technique will assume these numbers represent sort of like an ordering, incorrectly, of course. So the only way to use these then in a regression like technique is to dummy code these. Convert all these variables to switch type variables. Let me go back to Excel here to explain how this would play out and how you would go about doing this. Let's get our location variable in. The location variable has values 1, 2, 3, 4, and location values are Manhattan. I'll get the exact values here. Manhattan, Brooklyn, Queens, New Jersey. Now, let's just say we want to now make our dummy variables. A dummy variable is a variable that is a switch-like variable. It has either on or off. We can take a value of 0 when it's off and 1 when it's on. So dummy, we can convert to dummy variables. And so I'll abbreviate, you know, dummy as D. So D Manhattan would be one of the dummy variables we create. Another one could be dummy Brooklyn, and so on. So Queens and dummy New Jersey. Here we have it. We have our 4 kind of locations. And so let's just think about the logic behind this now. Dummy Manhattan can take on values of 0 and 1. And dummy Brooklyn, same 0 and 1, dummy Queens 0 and 1. Now, dummy Manhattan is 1 whenever the location is Manhattan. So this would be a 1 then. 1 because notice the location here is 1 there for dummy. The location is Brooklyn, then dummy Manhattan has got to be 0, Queens has got to be 0, New Jersey is 0. Similarly, dummy Brooklyn would be a 0 when the location is Manhattan, but 1 when it's Brooklyn, otherwise it would be 0. Same for dummy Queens also, we'll find the same playing out. For dummy New Jersey, I'm sorry, don't typo there. We would have, again, the same thing. So we have now represented here each of the 4 locations as 4 dummy variables. Now, as it turns out, the way the logic of dummy coding works out is that if you have information about any 3 dummy variables, you know the information about the 4th one. Consider assume for a second somebody didn't tell you about New Jersey. You don't know where the location New Jersey. So they just told you that it's Manhattan, it's not Brooklyn, it's not Queens. If it's Manhattan, you know, then dummy New Jersey has got to be 0 because it cannot be Manhattan and Jersey at the same time. Similarly, if somebody told you the location is not Manhattan, not Brooklyn, oops, not Brooklyn, it is Queens, then you know it's Queens, end of story, right? If it is Queens, then it cannot be New Jersey. In a way, given information about 3 columns, you can know the 4th column. Therefore, we don't really need the 4th dummy variable. That's a redundant kind of variable. In fact, when you're converting a nominal scale variable to dummy variables, you need not, if you have k levels in the nominal scale variable, you don't need k dummies. Rather, you need k minus 1 dummies. So we don't need the New Jersey variable at all. We only need these three. So let's just delete this one. And what we can do is we'll use the same recoding kind of process to dummy code Manhattan, Brooklyn, and Queens. So let me go back into SPSS. We have dummy variables at this stage. So here is our new variable transform into recode this into different variables. We're gonna, our new first one is going to be, first thing to do would be reset this menu, and then we'll go into input variables location, output variables dummy Manhattan. We'll change, specify the old and new values here. When dummy Manhattan, when the location is 1, dummy Manhattan is 0. I'm sorry, 1. When location is 1, dummy Manhattan is 1. Oops. Otherwise, 0. So all of the values and new dummy Manhattan is 0. So whether it's a 2, 3, or 4, that's all other values, dummy Manhattan would be 0. This made our typing, our clicking a little easier. And that's it. We'll repeat this process now for the other variables as well. So you go through this process, repeat this for, this time we'll edit the variable here. Let's say this is dummy problem, the second one. And change the values. If the value is 2, it's, take these out. Old value is 2 for Brooklyn. The new value here is 1. The dummy Brooklyn is turned on. Otherwise, it's 0. Okay, we got dummy Brooklyn taken care of also. Last one to do would be to do dummy Queens. Edit this thing. Change, specify the old and new values. When the old value is 3, that is when location is 3. The dummy Queens will be a 1. Else, it will be 0. Okay, this should do it then. Let's go back into our data view. And we can see out here we have now our 3 new variables created. They look as follows. And maybe you can, let's just verify this works for a few of them before we can move on. You see out here location as a column. So location is Manhattan. I mean, Manhattan is 1, Brooklyn 0, Queens 0. Location is New Jersey. All of them are 0. Location Jersey, we have all 3 of these as being 0, as they should be. Okay, so we have accomplished dummy coding then of our variables. There are instances when you might want to fix a skew distribution. It turns out that sometimes it is beneficial to fix a distribution that is, leaning one side, has a long tail. There is a whole family of transformations one can use called Box-Cox transformations. It turns out that a simple, specific type of box transformation called a log transformation tends to fix the distribution pretty good in general. So we'll kind of do this for a variable health3 and see how the distribution looks before and after the distribution is fixed. Go back to SPSS, and here is our variable health3. So here's our variable health3. If you recall, health3 looks as follows. We'll look at histogram of health3, and that's it. Here's a histogram of health3. We want to see what happens if we were to log transform the distribution. Would it be more kind of stable, bell-shaped or not? We'll kind of find that out. So I'm sorry, you couldn't see that. Here's the distribution. So we want to see if you kind of, again, try to do a log transformation, will this distribution be more stable? To do a log transformation, we're going to go to transform, compute variable. Here we'll say our new variable. Let's reset the old stuff here. Our new variable is called log health3. And this is simply going to be, we'll find health3 from the right. Now, the question is, again, what is log, right? Well, we learned logarithm. All of us have learned logarithm in school and college. But which kind of log? So there are many functions available here. Let's just look through what we find here. All, and type in L. Now there are many L functions here, including LG10, LN. They differ in that LG10 is log to the base 10, LN is natural log, or log to the base E. Let's use log to the base E here. You could either select it from the right, or you could just type in what the function is. When you select a function, it tells you what the function definition is. Like function works like this, ln, and whatever you want to put in there. So it's ln, and we'll go health3. We're also going to say +1 on here. And the reason for this is very simple. In our data, it's unlikely to be an issue, but it won't be an issue. But if at all you have any data that's 0 for any variable, and you do a natural log or log on that, you end up with a not defined sort of response. To prevent that from happening, you just throw in a 1 on there. So log of 1 is 0. Right? That's fine. Okay. And I'll say okay. Let's go in and examine our histograms now. One for, we already have health3. Let's get log health3 also in here and hit OK. So here is our old and new. That's the old histogram we had. And at the bottom here is a new one. I don't know if there's much of an improvement here in terms of the distribution. So yeah, these transformations don't always do the job. We hope that they'll fix the distribution, but they don't always, there's no guarantee they will always work. The next thing we're going to do here is we're going to bin a variable. So I'm not a big fan of throwing out data, but that's exactly what this exercise is going to do at this stage. There are instances where you might want to simplify the story by binning it into high and low. For example, could take McDonald's rating and simply bin it into low and high, because folks might be interested in knowing simply about what other people, who are the people who are rating it, below the midpoint versus above the midpoint. We're going to call a new variable McDonald's bin. The approach is very similar to one we have used before, so it should be quite familiar then. So we're going to go transform, recode into different variables. We'll take a variable McDonald's bin. And our new variable is going to be called McDonald's bin. And we'll specify our values as follows. We'll say when the old value is lowest through 4, the new value is a 1. When you go from 5 to highest, it's a 2. I'm thinking about this. She said less than 4, so this should be lowest through 3 because we said lowest, and this should be 4. So 4 to 4 to highest, and that should, and this should be our transformation. So 1 to 3 it is going to be treated as a 1, and so we then bin that variable here. So here's our new variable McDonald's bin, all the way on the right now. It only takes on values 1 and 2, depending on whether McDonald's rating is high or low. So the first 3 are kind of above 4, therefore they're classified as a 2 out there. There you go. Okay, on to, so we also know how to bin variables. Let's see, this is the last transformation we're going to do here. Whenever you use multi-item scales, you frequently want to combine multi-item scales into multiple items. You want to average them into an index, like a health index. So health 1, 2, 3, all are assessing health consciousness. So why not combine them into a health consciousness index? So we're going to do this, accomplish this by using the transform compute option to combine the different numbers. So let's go back to SPSS, and we'll go and we're focusing here on the columns health 1, 2, and 3. So transform compute variable, and this time we're going to call this health index, or just health. Health's good enough. And our expression is going to be the average of health 1, 2, and 3. So you can go and find a function that's going to be the average. So M, is there a mean function? There it is. So notice mean has a syntax, and that syntax is described out here as being mean with each variable separated by commas instead of parentheses. We'll follow that instruction. You could also just double click mean, and then it kind of populates that box with the function, and then type in health 1, or just move it in from the right, from the left. You type in, you got to make sure you don't commit any typos. Variable names are case sensitive. That's it. And if I hit OK, we're going to have a new variable called health. That is the average of health 1, 2, and 3. There you have it. Okay. So we have, over the last couple of slides out here, gone through a whole bunch of different transformations. Let me summarize everything then. So we have in the previous, in part 1 of this video, examine a coding schema, download data, label data. In this video, we check data by examining variable summaries, identifies the scenarios when you might want to edit the data, learn how to filter data, address missing data, and spend a lot of time transforming variables to make them sort of analysis ready. I'm hoping this was an enlightening journey, utilizing new software to accomplish a number of data preparation tasks. Thank you for joining me.